Why do we do this? Well, it actually brings into play another variable that's important to population modeling, and that's lambda. And lambda is sometimes referred to as the finite rate of increase. And it's pretty simple. It's actually 1 plus r. And remember, r is our geometric rate of increase. So it's 1 plus r. What is lambda a little bit more specifically? Let's have a quick look. Well, we can substitute lambda into the equation now. So let's revisit the equation where we left off, just here. So our population, one time step into the future, where we left off was 1 plus r times our current population, our starting point, you should say. So we can then substitute in our lambda value here for the 1 plus r term, because that's what lambda is representing. So our new equation then becomes lambda times nt, lambda times our current starting point population. And that will give us an estimate for our next time step into the future. Now, we could take this equation now and solve for lambda if we wanted to further define what it really means. So that's pretty easy to do. What we're basically doing here is dividing here the nt term, which would come over to this side of the equation. So lambda now is nt plus 1 divided by nt. Pretty easy. So if we don't happen to know per capita birth rate and per capita death rate, we can still estimate a measure of growth if we know something about one population size relative to the population size previously. If our pronghorn population has a lambda value of 1.2, we simply multiply that value, that growth rate, times the current population size to estimate what we expect that population to be like in terms of size in our next time step or our next time unit. So in this case, 1.2 times, let's say, a population of 100 pronghorn would give us what? We would expect 120 individuals in our next year. So lambda is used as a means of projecting a population at discrete time steps into the future. So for our pronghorn, we might be interested in knowing what that population will be like in 5 years or in 10 years. And in order to do that, we need one more quick bit of math. So let's return to our basic equation. This is the one we've been working off of, and we'll refine it a little bit more. So again, our population size estimate, one time step away, is lambda times our current starting population size. So we have our current population size being estimated here as N0. And let's say we want to know what the population size will be like in 3 years' time. So we've actually got 3 estimates here. We have year 1, year 2, and year 3. So how would we go about doing that? Well, if we go back to our equation here, for year number 1, N1 here, we have lambda, our lambda value, times our initial population size. And that'll give us a value. So for our second year is lambda times whatever our estimate was here. And our third value here, this is what we estimate the population to be like in 3 years, is lambda times the population estimate that we get from year 2. So what does that look like a little bit more specifically? Well, if we refine our N2 equation here a bit more, our N2 is lambda times this value for N1, which we know is right here. So that's lambda times N0. And we can refine our N3 equation here. So we have N2 that we'll substitute in for what we get here. So that's lambda times lambda times lambda n0. So this piece here is substituted from here, and this piece here is substituted from here. So there's a bit of pattern going on here, right? We have almost this nested pattern. In this case, you have lambda times lambda. So in year 2, you have lambda being squared. And in year 3 now, you have lambda times lambda times lambda. So you've got, wow, lambda cubed. There is a pattern emerging here. So that's for year 3. Let's jump back now and simplify our equation even further. So based on those values, based on those equations, we can refine our equation as this. Here, t refers to year. So t indicates year. So nt, the population size at any one year, is lambda raised to the t power times our initial or our starting point population. Going back to our pronghorn population, let's say we were able to study that population for some time. We were able to record the number of births and the number of deaths that occurred in that population, and we translated those into per capita rates of birth and death. So let's say our per capita rate of birth is 1.4 and our per capita death rate is 1.3. So with those values, then we can calculate R, right? So R is births minus deaths. In this case, that would equal 0.1. So it's 1.4 minus 1.3. With that value, then, we can calculate lambda, which is 1 plus R. So in that case, we would have 1 plus 0.1. In this case, would be 1.1. So we interpret lambda similarly to the way we interpret R. Remember, lambda is 1 plus R. So in this case, a stable population, one that's not changing from year to year, would have a value, a lambda value of 1. If that value was over 1, then we would expect an increase in population. If it was less than 1, we would expect a decrease in population. And the decimal points here almost relate to percentages. So 1.1 would indicate a 10% increase in population in our next time unit. A value of 1.2 for lambda, for example, would be equivalent to a 20% increase in the population the next year. So at the moment, our population of pronghorn is 100 individuals, and we're interested in knowing what that population will be like in 4 years' time. So we just use the following equation to make that calculation. And here's that equation right here. So again, what we expect our population to be in the future is lambda, our lambda value raised to that time period, times our initial population size. So for our pronghorn, 4 years out, we know that our lambda is 1.1, and we'll raise that now to the 4th power because we're at 4 years out, multiplied by our starting population, which is 100 individuals, and that should give us now a total estimate of 146 pronghorn that we expect given this lambda value 4 years out. Easy enough? So at this point, I'll pass you over to Terry, who will build a spreadsheet that will describe in more detail how the geometric population model works.